This video is to show the solution process to the review week number 6 problem coming from section 1.3, problem number 4. In this problem, it says, in 2 space, how many line segments can be drawn from a point on a line to a parallel line such that the line segments have the same length? Explain your answer, and does your answer change in 3 space? Explain. So I'm going to start in 2 space, and essentially the first part of the sentence in the problem is stating that we have parallel lines. It kind of says it in a not so obvious way that they're going to be between parallel lines because of the way that it speaks about from a point on a line to a parallel line. But essentially these are both going to be parallel lines. So we are looking at how many segments can be drawn that are the same exact length between these 2 parallel lines. So the first thing I'm going to start out with is just a very simple segment, and it's going to be a countable segment. So this segment is countable because it's horizontal and it's on the Cartesian plane. So I can clearly see that this is 4 units long. In case it wasn't countable though, I could go ahead and find the distance of it using GeoGebra, so I'm going to go ahead and do that too. And again, I've got that it's 4 units. Now, there are going to be an infinite amount of 4 unit length segments along these 2 parallel lines. And that is because parallel lines never intersect. So it has to maintain the same type of distance between the lines in order for that non-intersection to occur. Trying to showcase this and model what that's doing is you're basically going to be replicating the same segment an infinite amount of times, but that replication is occurring through a translation so that the corresponding angles between the segment locations would be equivalent, maintaining that preservation of image and distance. So we're going to go ahead and make a vector, which will allow us to translate. So I'm going to actually just make my first vector to B. And now I'm going to choose the option of translate by vector. So I'm going to go ahead and translate AC along this vector. Oops, that was a mistake. Okay, so let me just try that once more. We've got AC and this vector, and there we go. We've got a new segment, and I'm going to just see and double check, even though it's a countable distance again. What is that distance? And yes, it is 4. That would happen anywhere on this line as long as I'm just making a translated image between each segment so that I'm preserving those angles. But that's a countable distance. What if I were to do this amongst a distance that is not countable? Can I still do that same idea? And the answer would be yes. So I'm going to go ahead and choose a point that would not be in a horizontal or vertical location from another point on the line. So from AB, I'm going to go ahead and choose just a point here, and that will be point D. I'm going to connect those 2 into a segment, and then I'm going to measure the length of that segment, and I get 2.83. Now, in order to maintain the same idea that I can create an infinite amount of 2.83 unit long segments between these 2 lines, I'm going to go ahead and make a new vector. So in order to make that new vector, I'm going to actually just choose a new point to go to. So my vector this time is going to go from A to E. And now I'm going to go ahead and translate AD along the vector that I just chose. So we are going to select AD, and then we're going to select the vector. And again, we get a new line segment. And because of the translated values, everything should be preserved, including distance. So I'm going to go ahead and find the distance. And again, it is 2.83. Now, I could continue doing this all day long in 2 space, and the same properties will occur. So in 2 space, there are an infinite amount of segments that would be the same exact length drawn anywhere as long as the condition applies that the next segment you draw from the first segment would be a translated segment of the first. Okay. In 3 space, I took the 3 space option to show that this would, my 2 space idea would still occur in 3 space. So you can actually see my 2 space idea right here. in 3-space and it's still showing up the same way. But in order to fully investigate this in 3-space, I wanted to incorporate the coordinate value of z. So I'm going to go ahead and make some points that will allow us to get parallel lines in 3-space. So the first point that I'm going to make, so let's see, is going to be, I'm going to go over here. So we're going to do the point 235. Okay, that gives us that point. That's F. We're going to get this point, -2, oops, -2, 3, 5. And then we are going to also include -3, 4, 1. Okay. So now I'm going to take all that information and head back to my graph. So here we go. We're going to first connect the last 2 points I made, G and H, into a line. Then we're going to make point F, which is off the line, be parallel to GH. So using GeoGebra, all of this is possible, so I just need to select F in this new line, and now I have parallel lines. So the first thing that I'm going to do is go ahead and try to just connect G to F and see what that distance is and whether or not I can replicate it. So I'm going to choose the segment option. I'm going to go G to F. And then I'm going to need to do exactly what I've been doing this whole time, which is to create a vector in order to make that translation occur. So I'm going to make my vector just go to H, just for the ease of the problem. And I am going to choose the option to translate amongst a vector. So again, I'm going to be translating GF along this vector, and I get this new line segment. And before I had done this, I should have really looked at the distance of GF. So I'm going to go back and just look at that distance value, and that's 4. And then I'm going to just look at the distance value of the new translated segment, and I did also get 4. So this will show you that in 3-space the same idea will occur. And what's really great about this problem is it has a lot of real life pictures and scenarios that the kids can talk about in class. Just looking at this, they can start to see that it's a ladder formation, and that's the cool thing. So railroad tracks, ladders, etc., all of those types of ideas you can start to help visualize with the students, and I think that this is a great problem that really applies 2-space to 3-space. And you know, it's simple as far as the reason, but it definitely takes some investigating, and there is room for discussions and higher thinking. So I liked this a lot as a problem to use in my geometry class that I'm currently teaching. So whoever made this, excellent job.